Okay, whoops, I think I'm in the wrong place. Here we go, elimination. So we've seen induction already, and induction is the most important elimination principle, but often it's overkill. We might not need the induction hypothesis, and then we want to use one of the softer elimination approaches, or sometimes just more convenient. So I'm going to review a number of approaches to eliminate, right? And remember, eliminate is always about, you have a symbol in your, you have a predicate, or you have a, an assumption, and you want to extract information from it. That's elimination. Whereas introduction is when your goal talks about that symbol, talks about that predicate. So that's a difference. It's a different polarity, it's a different side of the implication, if you like. And we know most of these techniques already because they're the same for inductive predicates as they are for inductive types, right? So we've seen cases prime before, which is like induction prime, but without induction hypothesis. And there is also match. We've seen match expressions that can be used inside terms. Well, here we're going to be able to use match inside proofs, right, which are terms as well. So we're going to be able to write proofs with case distinctions based on match. And we've seen that already for, I think it was for or, to extract information for it from a disjunction, which was an inductive predicate. So in some sense, we're just seeing things that we've already seen, but then we can look at them with this additional knowledge that we have now of inductive predicates. So here's an equality. This is a nice little example because this is you often have a hypothesis that's an equality, and you're like, okay, I'd like to get rid of that equality. I would like to replace, all occurrences of R by L once and for all using the equality. And this is exactly what cases or cases prime offers, and it even removes the hypothesis H, which we don't need anymore, and also the symbol R. So you see it really, you start with this complex state here, which has PLR as the goal. You do a cases, and you just have PLL. Because the definition of equality requires both sides to be the same. You remember it was ek a. So if they're not the same, then they're made the same. So it's again an application of my favorite principle, was nicht passt, wird passend gemacht. Right? And then let's see. All right, the next proof uses classical, EM, so excluded middle, and it also uses OR. So here again, this is a little. It's just a constructed example to see things in action, right? So in this case, what do we have? We have, that we have two properties PQ, and we want to prove Q of A, right? Yeah, I think that's really an artificial example. I had forgotten about this one, but it's really an artificial example. Here I'm showing, first we say, well, either we have P of A or we don't have P of A. Then we do a case distinction on that. And then we're in the case where we have P of A, right? And this is the case where we have not P of A. So of course, this example is not provable, right? It's just a, it's just to show that you can do a case distinction on an arbitrary property. And in fact, here I've written it as a have, but what I could have done is just inlined it, right, with no have. And this we have seen before as well. Okay. Now, what also is quite convenient in practice is so-called inversion rules. So inversion rules, typically have this form here. They're lemmas that say if you have a certain symbol or predicate P, then you have certain conditions here. And you can do it as an if and only if. That's even more convenient because then you can do rewriting. So I'll show a concrete example. So this is an inversion rule for even, where we say even of n if and only if n equals 0, or there exists an m such that n equals m plus 2 and even of m, right? So what we're trying to write here basically is we're trying to say even minus n minus 2, right? We're saying either, to be even, either you're 0 or the number 2 before you was 0. But we cannot really trust subtraction because 1 minus 2 will return 0, and or 0 minus 2 will return 0, so it behaves weirdly. And also it's not in sync really with the definition. What the definition really says in some way, it says give me a number, an arbitrary number m, and if your number is even and n is 2 plus that number, then n is going to be even, right? So the for all in the definition becomes an exists when we write it as an inversion rule. And this can be done systematically for any inductive predicate. Even is again a good example. And this is the proof, which I'll just leave as an exercise. But again, you just have to be systematic. So this is an if and only if. So we do this kind of introduction. Then we have an implication, right? So well, I can do one direction maybe. Then we have even of n, right? I mean, here we don't know which direction to take. It's an or. Should we say n equals 0, or should we say that, whoa, there exists a witness such that blah, blah, blah. At this point, we don't know. We need to extract some information on even n. We need to find out why is n even. Is it because it's 0, or is it because it's a successor of something? So we do cases, and then in the 0 case, we end up with 0 equals 0 on the left. All right, so here there are lots of options, but we can take a simp to finish this off. And the other case, then we know that we need to go left now because k plus 2 is not going to be equal 0. So we need to supply a witness here, which is such that k plus 2 equals that witness plus 2. So I think that witness is going to be k. So we need to take a right turn first, which is what we do here, instantiate the witness, all right? And then, well, I mean, this is where lots of things would do it. I could also write CC here. I'm not pretty sure CC would do it. There we go. Right. And yeah, the other direction, I promise not to do it, but it's the same principle again. Right. And for those who prefer the structured style, then this is the structured proof, so with match. But again, if you don't like this style, just don't look at it. This is not, I mean, I'm not going to ask you to do anything like this in homework or, well, anymore. I think there were some examples like this in past homeworks, but from now on, you have full freedom on which style you want to use. Especially these matches here are quite tricky because you cannot just, you'd be tempted to match here on HN. And then what happens is it complains, you know, in a kind of weird way. Right. And this is a dependently typed match because we have a dependently typed, independent inductive type, and the matches need to also include the variables that change, right? So in this case, the n becomes 0. In this case, it becomes k plus 2. So it's quite tricky. It's explained, I think, a little bit in the guide. But my recommendation for this course, unless you really like this style, is to stick to tactics and not use these matches. I just showed them to show, okay, you can do them. You can, of course, construct a proof term for anything.